Good morning, everyone. This is my senior project presentation on the design of a syringe-based buoyancy engine. So the motivation for this project was the use of buoyancy engines in AUVs as a low-power depth control method. So buoyancy engines work by either changing the system mass or the system volume, and this enables vertical movement through the water column. And a very simple, common method in low-cost gliders of achieving this buoyancy change is through mass change, specifically through a syringe system. And so the goal of this project was to design a syringe-based buoyancy engine that was capable of responding to external pressure to accurately reach a command depth. And the goal for this project was to minimize the cost of all components. So the first set of calculations that I did to help make design decisions was terminal velocity calculations, which, as you can see from the skydiver example, whenever there's an object falling through a fluid, it will accelerate until the drag force is balanced by the gravity force, or for an object in water, the buoyancy force and the drag force in the upwards direction is balanced by the gravity force in the downward directions. And these calculations were very useful in making design decisions because they helped to determine the cross-sectional area that I would need to be able to get to a certain terminal velocity, the enclosure volume, and the syringe capacity. So I basically set a terminal velocity that I thought would make sense for a testing environment. So I used a goal terminal velocity of about 10 centimeters per second. And then I just performed various calculations in order to be able to find optimal enclosure size and expelled mass. And I just did this for different iterations of enclosure sizes and syringe capacities for each milliliter of expelled mass, what the terminal velocity would be. And in order to do this, I did have to estimate a drag coefficient. So I found an estimation for a cylinder moving in laminar flow. I assumed laminar flow just because the object at 10 centimeters per second would be moving extremely slowly. So I found an approximation for a cylinder moving in laminar flow with the flow parallel to the axis of the cylinder. And so my original idea for the project was to use a large syringe system and then to have the enclosure basically fitting pretty much snugly around that syringe system. My terminal velocity calculations revealed that a larger enclosure size was needed and that the expelled mass should be relatively small, around 5 grams. And the idea is to maximize the positive and negative potential buoyancy change. So the system was designed to be neutrally buoyant when the syringe was half full. So a expelled mass of 5 grams would relate to a 10 gram total, or 10 milliliter total syringe. And then also these calculations suggested that a large projected area was required in order to generate enough drag to slow the system down. And the added mass and the terminal velocity calculations that were most ideal was for a 15 centimeter by 15 centimeter syringe, which is about 6 inches by 6 inches, which is slightly large to be effective in a testing environment. So I downscaled a little bit from my final product, but the calculations were necessary in finding out the basic size of the enclosure and the relation of that enclosure to the size of the syringe. And throughout the design process, I did change the exact size of the enclosure a couple of times, but neutral buoyancy calculations were performed for each iteration to make sure that I would be able to achieve neutral buoyancy, because these calculations determined how much ballast weight needed to be added to the system. And then once the components were finalized and I had my final design, that determines the exact ballast weights that I used in my system. And the idea was also to keep the center of gravity as low as possible for stability purposes, just because for a fully submerged object it is stable as long as the center of mass is below the center of buoyancy, and it is more stable the lower the center of mass is. And I used fusion to be able to locate the exact center of mass and compare it to the center of buoyancy for my final design. So for my actuation methods, the original idea was to use a stepper motor to use the syringe system, just because that's commonly used in those types of systems, and stepper motors are very precise. And the idea was to use the Lowland 32 Lite microcontroller. There were a couple of problems with using the stepper motor with the Lowland 32 Lite. One of them was because even with the kind of smaller, simpler stepper motors, you still need a relatively high voltage, and that would complicate the system, because you have to add a signal converter to be able to communicate from the microcontroller to the stepper motor, and also potentially voltage regulation depending on the size of the battery. And also the more inexpensive low power stepper motors are very slow, so it would take a long time for the syringe to be able to empty and fill. So the stepper motor idea was ultimately scrapped. I also looked into using linear actuators, but I was running into a couple of the same problems just because of voltage requirements, and also just using the space inside of the enclosure inefficiently. The system that I eventually decided to use to move the handle of the syringe is a rack and worm system, and this is much better for this system because we would be able to use a micro DC motor, which would run on lower voltage, 3 volts, and that would be able to be powered directly by a small 3.7 volt battery. And you also configure that with a linear potentiometer to be able to track the position of the syringe and prevent it from being overextended. And the mount on the right here was the original design that I 3D printed to be able to mount the motor and the linear potentiometer and the rack and worm system. And then there's a slightly modified version on the left that I actually used to mount to my PCB in my final design. And the idea of using the rack and worm came from this YouTube hobby project. So this is a circuit diagram. Once I knew that I was using a micro DC motor to move the handle of my syringe, I looked up motor drivers and ESCs to find out what would be best to be able to control that motor. And I ended up using an H-bridge driver for bidirectional motor control, and that would be controlled by the microcontroller, which would also take readings from the pressure sensor. It would also monitor the position of the syringe using the linear potentiometer. And the idea for the PCB was for everything to be mounted to the lid of the enclosure. So the PCB would be mounted directly to the lid of the enclosure, and for the pressure sensor to be mounted underneath the PCB, so they could be mounted directly onto the lid. And the kind of odd shape of the PCB was determined by the ballast weights that I ended up needing to get to neutral buoyancy. And so the PCB here is mounting the H-bridge motor driver, the microcontroller, the battery, and the pressure sensor, and also the through holes for the linear potentiometer. And in the process of designing my PCB, I decided to scale down my microcontroller to the more compact Xiao ESP32 S3 board, just because it fit much better in the enclosure. So I also had to design a spacer to give enough room between the pressure sensor and the lid of the enclosure. So this little polycarbonate piece has a hole drilled into it with a chamfer to be able to mount the pressure sensor with an O-ring. And so that piece was attached directly to the lid, and the spacer kind of fit over that piece. And so it kept the required distance between the PCB and the lid. And it also served as a mount for the ballast weights that I needed for my system. And once I had that design finalized, I also designed some feet for the system to kind of set on, which would protect the tip of the syringe in case it came into contact with the bottom of the testing tank, and also just to make it easier to access and store the system. and the feet screwed onto the spacer and through the lid. So once I had that, all of those designs finalized, I soldered everything to the PCB and tested the linear actuator on its ability to move the syringe handle up and down. One of the problems that I had when I was originally testing the rack and room system was that the syringe handle was bending backwards as it got close to the upper extent. And this system, using this mount and the linear potentiometer, provided enough stiffness for the handle of the syringe to be able to be moved up and down smoothly. And I used a code that just sent the syringe handle up and down constantly to kind of refine the upper and lower limits of the potentiometer to be able to set the limits of the syringe handle. So for the final design, this is just a testing of the syringe handle, making sure that it's moving up and down smoothly. So once I tested the actuator and the pressure sensor thoroughly independently, I waterproofed everything by adding silicone to the penetrations where the syringe penetrated through the enclosure lid and all of the screw holes. And I mounted all the ballast weights, and I also used some other smaller ballast weights to fine-tune the mass to be able to reach the exact mass I needed for neutral buoyancy. So I waterproofed everything. I tested the system to make sure everything was watertight. The original plan for the project was to kind of use a PID algorithm to be able to effectively get to the command depth. But first I tested out just a very simple code that would set a command depth, and then whenever the system was above that command depth, the syringe would fill up with water so it would sink, or whenever it was below the syringe handle, below that command depth, the syringe handle would be fully retracted and it would rise. So this was effective in reaching the command depth. Unfortunately, the system is that's a screw-on enclosure lid, and after I was running this depth, the system actually flooded because there's so much weight mounted to the bottom of the screw-on lid that even though it is watertight, it is sensitive to pressure or kind of squeezing. So any sort of irregular pressure would cause that seal to be broken. So I wasn't able to test as thoroughly as I originally anticipated. So that is something for future work and improvements to the system to implement the PID controller that I prepared to find the optimal gains for this particular system. So, and then also configuring the system to work through Bluetooth and kind of implementing a more permanent watertight seal. So the components for the system were chosen to be kind of as low cost as possible. It was funded through Eagle Spur, and most of the additional expense came from finding a specialized testing tank that was kind of skinny enough and large enough to be able to test effectively, and ballast weights, and finding an enclosure that was exactly the right size to fit the components that I needed, but the electronic components themselves were relatively inexpensive. So the skills I learned and used, fluid mechanics and the terminal velocity and drag coefficient equations, electronics and PCB design, a lot of CAD modeling, programming and control algorithms, PID algorithms specifically, and then a lot of 3D printing, and also time management and getting things done on time, problem solving, and communicating our progress weekly. The unexpected challenges, I ended up needing much more ballast weight than I originally anticipated. It was also difficult to kind of fine-tune the ballast weight to get exactly the weight that I needed. And also waterproofing later on, that was a bit of an issue. And the biggest overall constraint was just time. I ended up running out of time to be able to effectively tune and test the system completely like I originally intended. questions?
While people think about questions, why don't you bring your test tank and all your hardware up front so you can have it right there.
It's not set up to actually. It's the finished design.
So just to clarify, the lid with the weight on it just bowed a little, which allowed it to leak, and that's why it's loaded?
Yeah.
Okay.
Well, I don't think it was actually bowing. It was just any sort of even squeezing on the top. It was just really sensitive to.
Separation.
Yeah. So, you wanted all of the PCB or parts to be mounted on the lid, so it could be easily taken off.
Right.
If you were to do a redesign, would you want to try and remount it on like the bottom side so the lid isn't being pressed on by anything, or would you want to try and like figure out a way to seal it?
I think the problem was I kind of needed to get in and out of the system while I was making sure that everything would work properly. The best way to do it was configure it through Bluetooth to where you could seal the lid and not have to open it and close it. I do think it is better to have everything mounted directly to the lid.
The projects are similar to Corey's. How do you try to use what you produce?
So I did, Corey's work was very useful in understanding the terminal velocity calculations. He used changing volume. So the idea for this was to use changing mass through the syringe. So that was kind of what, but it was definitely, I used Corey's work on the terminal velocity and force balance equations to be able to find the enclosure size that would be ideal.
There was one thing you could go back and change throughout this process and your project specifically, what would you change?
I would just do everything quicker. Yeah.
It's always the goal.
What do you mean by quicker?
Just come up with calculations, like focus on making sure every week that, I have fully supported, well thought out ideas and not letting, simple design decisions kind of drag on, just kind of committing to, well thought out design decisions throughout the process.
Any other questions?
Sam, after the system got flooded, have you attempted to find a solution, or have you tried anything to test it again?
The problem was the potentiometer, I believe, got damaged because I tried using the syringe handle and it doesn't work effectively. Whenever it gets to one of the limits, it just keeps on wanting to keep going, and unfortunately this happened literally Monday, so it's just such a time crunch that I wasn't able to redesign. I think I would have configured everything through Bluetooth and formed a more permanent seal and tested it through that if I had enough time to do that.
And in terms of your housing, would there be a simple solution to kind of use a different housing which doesn't have the problem of flexing? Any suggestions there?
I think you could use, you could design an O-ring, like your own lid with an O-ring, and that would probably be more effective, or just use silicone or some other sort of seal around the existing lid.
Because I almost feel like we discussed using maybe a glass jar, and I kind of advised you not to go there. it may have been actually ultimately more stiff, right? And you just have to be careful that we don't drop it. Because I think it is likely that somebody else will attempt something similar to your glorious float. So that is good learning exercise for all of us. And we can hopefully eventually get to a float. Because you definitely brought it farther than, no offense to you, than where you got it to. So hopefully each iteration we will get a step closer to a final product. So maybe third time is the charm. All right, if there are no more questions, then let's give time.